today we're going to talk about a few things. It's a good idea if you can actually see the screen, so I'll put the screen up. So we're going to talk about two things. First, we're going to cover references, understand what references are in C++. After that, we're going to cover dynamic memory allocation. If we can't finish it today, Monday you have a class, right? You have a Monday. We're going to complete it on Monday. But I think we're going to be done today, so I don't think anything's going to be left. OK? So for those who are not here and are listening to the recording, if you are not in labs in OOP244, you will not be able to submit your workshops. You have to submit your workshops from a lab computer. Today is an exception because we missed this lecture. Today is a lecture, so that's why I'm giving you a chance to submit it after. OK? Apart from this, any workshop that you submit has to be done from one of these computers. You cannot do it from your laptop. It has to be from one of these computers. OK? That's that. For the test that you have the next day, for the test that you have, oh, actually, let me just start the recording over here, too. Yeah, so as I was saying, you have to be present at the workshop, at the lab, to be able to submit your workshop from Seneca computers. Today is an exception because we missed the lecture. We're going to do the lecture today, and that's why you're going to get it. You're going to be able to submit till midnight with no penalty. And after midnight, it's closed. You cannot submit anymore, OK? Unless you are an accommodated student or you get a personal extension for any reason. OK? The submitter program knows who has an extension. That's why -do is an important thing. If you do -do, it tells you what is your extension. And again, if you are listening to this recording, it is important to know if you have any difficulty or if you have any problem understanding or anything that is preventing you to study and learn, please go talk to student council. It's very possible that you would be eligible for accommodations. And if that's the case, like if you have any problem, any difficulty that you cannot study properly or you don't study as fast as others and you need help, go to student council and apply for it. They're going to lead you, tell you where to go and what to do. And if you are eligible, you're going to be accommodated. And if you are accommodated, everything will be set based on your accommodation that the school is going to give out. It has to be something that comes from school. So if you haven't done that, it's a good idea to do it. Now, let's start. We are going to talk about references first, OK? In IPC 144, we learned that in C language, we have something that acts like a remote control, which essentially anything you want to control remotely, you can use a remote control for it. That remote control is called what? That remote control is called what? Anyone? What is that remote control called? What is that remote control called? You remember? It's called a...
What was the question again?
Now you have the microphone, you're listening, huh? OK, we said in IPC 144, we learned that if you want to change something remotely, something that is not in your function, it's somewhere else, and you want to change it, you have a remote control that you can change them. What is that remote control called? It's a pointer.
Oh,
Yes, it's a pointer. Pointers are used to change things remotely, things that are not in your access, in your scope. For example, we said, like, for example, if I have over here a function foo over here, and this function foo wants to change something in main. So in main over here, I have integer value. And in foo, if I want to change this value, I can pass over here an integer pointer called VPTR, let's say, and I can say change the target of VPTR and add 1 to it. And by doing something like this, sorry, pointer, yeah. And by doing something, I can actually change the contents, the value, the value of this variable and in function foo, which means now I can say foo address of var, and if I see out var over here, then obviously var will be 11 because it's been added by 1. You follow? That was pointers in IPC 144 that we learned. And if we didn't, then it's a good idea for me to send you a link. So how many of you have difficulty with pointers? You do? Okay. Pardon me? Difficulty means like you think pointers are a big deal and it's difficult to handle and stuff like that. Okay. Long time ago in galaxy far, far away, I did a crash course on IPC 144. So one Sunday, we started at 7 o'clock in the morning, or 8 o'clock and 9 o'clock in the morning, till 5 o'clock in the afternoon. I went through all IPC 144. I reviewed it. You want me to make that available to you? Anyone is interested? Okay, so I'll do that and I'll put it in our repository, in the notes repository. Maybe it's already there, is it? Let me take a look. Fardad's notes. It's not here, but if you go to Notes Archive, you see that? If you go to Notes Archive, and for example, go to the previous semester, 2251, you see it says IPC 144 Review. If you click over there, and also it should be in the README files over here. You see that? Review recordings, and if you click on part 1, I'm hoping that it's, yes, there you go. This is something that I have done, I think it was during COVID. You look at me, I'm in my room actually at home. Okay, so yeah, so this actually covers everything in IPC 144 from beginning to the end. Go to the archives and look at the last one, and you click on the videos, and all the code written is in the review. So you can actually go through it and see what it is. And I think one of the students enough that actually timestamp it, said that at this time it's this, so you can actually directly go to pointers and see what they are. But anyway, so that's how pointers work. So essentially, we said that a pointer's job is to point, okay? Everything in C language is passed by value. Everything in C language, everything is passed by value. There is no pass by pointer. We don't have such a thing. That such a thing doesn't exist. Okay, pass by address. You can pass by value. Now you can pass the value of the variable, or you can pass the address of the variable by value. It doesn't make any difference. In here, I'm going to say at line 11, I'm saying foo, pass the address of var to foo. In foo, I'm creating a variable called VPTR, that is getting the address of the variable. And then I say target of VPTR++, it means go to where that address is pointing. Remember, say the right name, and you'll understand what's going on. If an asterisk comes after a type, together they mean pointer. Don't call it integer star. This is an integer pointer VPTR, which means VPTR is a variable, like any other variable, integer, double, character, but it's a pointer. Okay, its job is to point. So that's an integer pointer, okay? When you put an ampersand beside something, it's called address of. So address of var. It means where var is in memory. If you don't leave it, print it, you'll see. It's going to be a ginormous number that is actually a byte number in your memory. And when you see asterisk beside a variable, you can 100% be sure that variable is a pointer. And that asterisk means target of. So this means target of VPTR +1. This means pass the address of var to foo, okay? And foo will receive address of var and so on and so forth. To receive an address, what do I need? I need a pointer variable. Now that pointer variable is nothing but an integer. Again, if you don't believe it, just print it. If I go over here, see out VPTR, and I print that out, you will see that that value is printed. You see that value? That's essentially a hexadecimal value for the address of where that little integer of mine is in memory. And if you want to know exactly where it is, we know how to cast, right? So I can simply say over here, long, and I do that, and I print it out again, and this time it actually shows the actual integer. So if you can read that number, that's the address of my integer in my memory. Where it is exactly. You have to count from 0 with bytes. When you reach that, that's my integer. Okay? Got it? Okay. So that's how C language referred to, that's how C language used a pointer to change remote values. Because when I'm in main, I cannot change the contents of main in foo. Therefore, I have to pass a remote to foo, so foo can change the value of mine. That remote, we call it a pointer or address. We good? Okay. In C, we have a new way. In C++, we have a new way we didn't have in C language. So, what is my name? Anybody knows? Fardat, right? From now on, please call me Freddy, because it's easier. Okay? Let me do that? Are you okay with this? Okay, she's yeah. Like, I don't know if I like it or not. Frank is good. Okay, Freddy, right? So if you call me Freddy, what's going to happen? If I tell you Freddy is going to teach C++, what does it mean? It means Fardat is teaching C++, right? If I'm going to say slap Fardat in the face, Freddy's going to get slapped in the face, right? Do we have two people or one? One per person with two names. One is Fardat, second one is an alias. Do we understand this? Are we all okay with this? We have that capability in C++. In C++, I can actually give a variable a new name. I don't have two variables. It's this good old variable that I had, but it just is referred to by something else. How? Like this. So let me just save this. So I'm going to call it over here 0, 1, and I'm going to call this, what am I going to call this? Tell me. I'm going to call this over here accessing remote variables using pointers in C.cpp. Okay, so that's C. It has nothing to do with C++ actually. Okay, now we're going to come back over here. Now let's get out of here. We don't need, yeah, we don't need that. So in here I have integer var. I'm going to set it to 10. Okay. Now what I can create, they call it a reference. So that alias, that my name is Fardat, call me Freddy. Freddy in C++ is called a reference. So you can literally call that thing a reference. How do we create a reference? How do we create a pointer to an integer? We put an asterisk afterwards, right? How do we create a pointer to an employee? We write employee and we put an asterisk afterwards. How do we create a pointer to a car? We write a car and an asterisk afterwards. And we call it a car pointer, an integer pointer, a double pointer. Now I want to create a reference to an integer. How do I do it? You write the int to know what is it referring to. So int, and a reference is ampersand. It's not asterisk. If the ampersand comes after the type, together they mean reference. It has nothing to do with address or anything. So an ampersand after a type, it means this is not a new variable. As a matter of fact, if I do something like this and I call this A and I put semicolon, it's going to give me an error. It says, you just told me you want to create an alias. What is the alias for? Can I say Freddy please call, no, I can't even say it in English. Can I say, Freddie is a new name? You're going to say, for what? For what? Who? Right? It's the same thing. When you have a reference, you have to tell what is it reference to. Now, if I write over here, actually, let's call it R, so it kind of sounds like a reference. Now I'm going to say var. It means now var has a new name called R. R and var are the same. They are no difference. They are identical. They are the exact same thing. You want me to prove it to you? This is an easy proof. I'm going to say cout R's address. I'm going to say long address of R. And in here, I'm going to say var's address. And in here, I'm going to say address of var. So if I told you my address is 34 Yonge Street, his address is 34 Yonge Street, what does it mean? We live in the same building, correct? We are the same. We have the same location in hand, correct? When two addresses are the same, it means it doesn't matter what you say. It's the same place, correct? Same thing over here. If I actually print these two and I look at the outcome, I will see that the address of var and R, they are identical. They are the same thing. They are not two different things. That's why if I say over here cout R, or if I say cout var, the outcome is both 10. No difference. If I set R to 100 and I cout var, hundred's got to get printed. They are the same. Do we understand this? So you just now learned how to give a new name to an already existing thing. That thing can be anything. Are we good with that? Are we okay with this? You okay? Okay. Now let's see what are the side effects of this. And it's the same thing with anything. I can write over here struct car int number of seats int, I don't know, int, yeah, number of seats. That's what else? Int, give me another thing for cars. What do I do? I don't want to have a character thing. Huh? It's always 4, isn't it? Yeah. A number of passengers. Right? So I have a car like that. Now if I create over here struct, if I create over here car C, and I'll set that car C to 4 and 2, it means it has 4 seats and 2 passengers, right? I can simply say car reference CR is equal to C, which means CR and C are the same. No difference. Now in here, if I say cout CR dot number of passengers and in here I write CR dot number of seats, what I'm going to say is what I'm going to see over here is exactly what I set the, why is it not running? What it's going to come out is exactly what I set the other one to. You see that? You follow? We're okay with that? Now we understand how references are created? Are we good? All right. Now, next. So that's reference introduction. So So what is this function doing? It's printing a value, right? Right? Okay. So if I run the function, if I write over here print int x is equal to 1, 2, 3, and I'm going to say print x. Then I'm going to say print. Okay, and I run the program. We know what it is. It's just going to print 1, 2, 3, and yada, yada. Right? Are we okay with this? Why did I write this? To tell you how functions are called in C and C++ language. When you see a function is called, what you do, you write the prototype of the function in front of it, and you put equal to the value that you're passing. This is literally how that function is called. Literally. Got it? So when you are passing an argument, essentially you're passing a value to a function. The argument of that function is initialized with your value. It's always like that. So what is the second function call? The second function call will be this. Which means here, val is initialized by the value of x. In here, val is initialized by 532, yada, yada, yada. And this means you follow? So essentially, var will be initialized by address of x, val will be initialized by 54321, and val will be initialized by x. Therefore, the stuff happens the way we do see them happen. Are we okay with this? This is how the functions are called in C language. Do we understand that? When I say C, it means C and C++. Fantastic, Mr. Bombastic. So in here, I'm going to go 0, 3. I'm going to call how functions are called in C and C++. .cpp. Okay? Are we good? All right. Now that we have this, and now that we know how references work, let's do this. Remember that add one thingy that we have written? So in here, I'm going to say add 1, and I'm going to put x. And in here, I'm going to say cout x. If I run this program of mine, we know that it's not going to change. It's going to be 1, 2, 3. Why? Because when I call the function is called like this. So essentially, val becomes a copy of x. Are we all okay with this? And this val, that is copy of x, will be added by 1. Good for val. When the scope is over, val's going to die. It has nothing to do with x in here. Are we all okay with this? Are we all okay with this? Good. But what happens if I do this? If I make val a reference, you're going to tell me, hey, But you told me that val is going to get initialized. And I'm going to tell you, yes, it will be initialized, because that's how the functions are called. If I do this now over here like this, you will see that val in here becomes a new name for x. So when you say val plus plus, you're actually saying x plus plus. Therefore, when you run this, this happens. That's the beauty of references. You don't have to pass address schmatters anymore. You simply create a reference, and in that scope, that reference becomes a new name or a reference for something outside of that scope. Anything you do to it will get applied. Are we okay? Are we okay 1? Are we okay 2? So, okay, that's references. We're done. Okay? And that goes with everything. Now, this reference has some consequences. It has some, I can do some nut stuff with this. So I'm going to say 04, passing references to functions. Now I'm going to do something nuts, people. Something absolutely crazy. Take a look at this. And in future, you're going to see this nuts thingy is going to come in handy. I'm going to call it over here, what the heck. And to follow that thing has to be lowercase. Okay? And in here, I'm going to say return an integer reference. And all I'm going to do over here is return val. We good? Are we good? I'm not doing anything in that function. I'm just returning the name that I'm returning out, right? So what does this thing mean? Integer reference. It means a reference, right? That means the function itself becomes a new name for whatever it's sending out. So take a look. If I say cout, what the heck, x, what's going to get printed? 1, 2, 3. We know that, right? Easy. Correct? Are we good? Now I'm going to do the crazy thing. You know what's the crazy thing? I'm going to say, what the heck, x plus plus. That's crazy. Have you ever added 1 to a function? What the hell is that? When you follow the logic, it makes sense. Because what the heck is returning is becoming a new name for val, correct? And val is a new name for x, correct? Therefore, what the heck is a new name for x? Therefore, it works. So if I say cout x over here, you will see that it actually becomes 124. Okay? You don't need to fully understand it now. Go home and digest it. Okay? For some reason, as soon as I start teaching, all the spammers in the world start calling me. I don't know what. Sorry, I have to leave my phone on because I have an elderly mother and I might be for help. So that's why it's always on. Sometimes I'm going to say, excuse me, and I'm going to go run out. Okay? So that's that. Are we good? So remember, reference can be anything. Even a function can be a reference. And later on, we'll see that that comes extremely handy. Okay? But remember this, and I'm going to call this thing, and I always do, and I'm going to call it crazy reference. Crazy reference.cpp. Okay? And your job is to reflect on it and tell me what this crazy reference is. I want to see it in your reflections for workshop. Whatever workshop that you have that you're doing references in. Okay? So, anyways, that's that. Next thing that we are going to talk about is dynamic memory allocation, DMA, okay? And it all uses pointers. My apologies. So you need to know pointers. And I'm going to go through it, go through the whole thing, and I explain to you how things work. Go through the weekend, go through that IPC 144 review, spend 4 or 5, I think it's 4-hour lecture, 5-hour lecture. So go through it, and believe me, if you have some weak spots in IPC 144, that comes really handy. Okay? And if you see it doesn't tell what the timestamps are, okay? Go back in archive. I've done this many times. You'll find one that has the things in there. So you can actually jump directly to pointer explanation, stuff like that. So Notes Archives has lots of stuff in it. Are we good? All right. What is a pointer? A pointer is a variable that holds the address of something else. If I set the variable to something, that something must be an address of something else. If I want to not to work with the pointer, but work with what the pointer is pointing to, I use the target of operator, which is an asterisk. If I say target of something, that means. Also, you know that arrays are pointers, right? Arrays are literally pointers. How they are pointers? Essentially, when you're dealing with an array, array essentially means you have a bunch of stuff back to back sitting in memory. So this thing that you see over here is like series of integers. How many? I don't know. 1, 2, 3, 4, 5. Sorry for my lack of artistic values, but these are, let's say, and they're all equal. There are five integers, right, in memory. And to be able to access them, what do? They create a pointer and make that pointer point to it. And let's say I call this A. That's what an array is. So 1, 2, 3, 4, 1, 2, 3, 4, 5. This is 6 integers, right? To actually code this in C, you write this. You write integer A6. And the outcome of what I have written is the diagram that you see. So if I actually set these things to some values, so if I put over here six values over here, because they did not see is a low-level language, it doesn't have a construct for this. It created an array using all the facilities it already had. So it says, I already have the concept of a pointer, which is essentially a variable that points to an address, right? So when you write something like this, it's actually a combo. It creates a pointer called A somewhere in memory. Then it creates 6 integers back to back somewhere in memory, puts the address of the beginning in there. So essentially, if I say target of A, what's going to get printed is the first element. That's how it works. So this essentially means, and for everyone to be able to work it without the knowledge of pointer, they did that. That essentially means from address A goes 0 integers further. What does it mean? The first one, right? If they say A1, it means from address A past 1 integer, which means the second one. And that's how everything. So essentially, this means these 3 are the same. all these three will print 100 for you. Target of A, 0, or target of A plus 0. They're all the same. And if for these two, I can even do this. I can write 3 and right over here 3. These two are identical. It's the same thing. You see? Both 400. Yes? If I say, sit on that chair, why you are not sitting on all 6 chairs and only sitting on the first one? Ta-da! It's the same thing over there. Why should it print the whole thing? Why did you get that idea? Why do you, when I tell you get the 4th one, why do you think 5th and 6th is for you too? Where did you get that idea? Again, never, this is actually very good, and thank you for that question. Everything in C language is manual. It never does what you expect it to do. You cannot say print an array and print the entire thing. If you want to print the array, you have to go one by one and print them. Because it's not one integer, it's 6 of them. If I told you there are 6 houses and I showed you the first one, you're not going to visit all 6 of them. If I go to the 3rd house, you go to the 3rd house. It doesn't matter how many houses are in the street. It's the same thing with an array. When you have a series of integers, whichever you refer to, that's the one you're dealing with. The fact that they are back-to-back in memory has nothing to do with anything. Okay? And now you know 3 over here doesn't really mean 3. Because you know an integer has 4 bytes, right? This 3 actually means 3 integers. So this 3 is kind of different with pointers with regular integers. Okay? But again, this is just for you to remember that pointers and arrays are the same thing. The only difference is that a pointer points to a single thing. I'm going to say this table. An array, I'm going to say these arrays, these chairs. When I say these chairs, that's an array of chairs. And the problem is that C language doesn't know how many. When I say these chairs, you have no way of counting because there are unlimited number of chairs in memory. That's why I have to tell you these 4 chairs. Otherwise, you're going to go forever in memory. And segmentation fault and code dump and stuff happens, right? So that's that. Are we okay down to this point? Okay. Sorry I'm not giving you a break today. We started late, so consider that your break. All right. So that's that. So this is kind of an intro reminder of what arrays are. And then we are going to talk about dynamic memory allocation. So we said that when you create an array, in this case 5, a pointer is going to get created in memory. That's A. And then 5 integers are going to get created in memory, right? You see that? Exactly what you see. That's exactly what you see. And that's exactly what is created. You see that big box that I've written that said the executable program? That's actually what happens. When you create the 5 integers, they are all built in inside your executable. So when you execute your program, the array comes with your program, everything into memory. You work with your array, and when executable is done, the execution is done, operating system takes the executable away, and with your executable goes the array. Are we okay with this? And that is why you always have to know how many things you want. Like if I told you, get integer numbers from a user and print them in reverse order. You can't write this program. You're going to ask me how many. I say I don't know. So you're going to say, I'm going to put 1,000. Nobody's going to put more than 1,000. And some lunatic puts 2,000. And the program doesn't work anymore. So there is no way to write a program that works, for sure. Because any number you put, somebody's going to put one more. And that's going to ruin your program. Right? Why? Because everything has to be inside the executable. You have to think about it when the program compiles, not when the program runs. Appreciate the difference between the two. When you compile the program, that's when you're inserting the array inside the executable's belly. But when the program runs, there is no compiler. What you have is what you got, and that's it. You can't do anything about it. Do you understand this? We're about to change that. And that's called dynamic memory allocation. With dynamic memory allocation, we do not actually allocate the array. Because we know an array is essentially a pointer and a bunch of things, we just create a pointer. And when the program runs, we ask the user, how many integers do you want? User says, 2,000. Then you ask the operating system, give me new 2,000 integers. And the operating system, while your program is running outside of your executable, will put those 2,000 and give you the address and put it in your pointer. Now you have an array of 2,000 things. And you work with it. Life is beautiful. If it grows more than that, you can simply create 5,000, copy everything from 2,000 to the new 5,000, throw away the 2,000, now you have 5,000. So on the fly, you can change the size and do anything you want. Sky's the limit. How it's done? It's done like this. So, and it's called heap. So it's actually created that piece of memory that is shared by all executables is called heap. So what you do, you create integer pointer A, and then you say, now I did it, I initialized it. You don't have to. You can just create the A, and 6 lines later, 100 lines later, you can say A is equal to new. But you're going to say new int5. This new int5 doesn't happen at compile time. It happens at runtime. Therefore, you can decide how many integers you have. And all the things are getting created over here. Now, when this executable, the top one, is gone, everything will go out, correct? How about the second one? When the program ends, what's going to get out of the memory? What happens to this? It remains in memory, and that is called memory leak. That is why when you have that wireless router at home, and after 3-4 weeks that it's working, it doesn't work, you call Rogers and say, unplug it and plug it back in. Why? Because they want everything to get wiped out and you start. Because if you have leak, every time the program runs, it creates a new 5 integers and a new 5, and it keeps doing that. Those things never die. It stays in memory. And unfortunately, at the end, it's going to fill up your memory with garbage, and you have no more memory to run, and your machine hangs. And that's where you reboot. Because those wireless stuff, they have very small piece of memory, and it's written for just wireless stuff, or the router that you have, or things, or I don't know, all the stuff that you have to unplug and plug for it to work. That's what happens. It means the program has leaks, and that's why they have firmware updates. Every time you do a firmware, they fix all these things that they have done. So our job will be to learn how to allocate memory and how to deallocate it properly, and that's what we're going to teach today. You have a question over there? For removing it, yes. Oh yeah, let's say you're working for Google and something goes wrong, you're just going to restart Google?
No, assume that all the garbage data will be in RAM.
Yes.
RAM is short
Yeah.
memory, and that's why you also can start and
Yeah, but you can't do that. You can't write a program. So you're going to say, I'm going to write a game for you. It's a game that is, you're driving a car in it. And I say, if you see it doesn't work, just stop the game and restart the machine. You can't do that.
can't you just save the program and just go for R write and come back, open
Yeah, especially when you are flying an airplane, let's do that. The computer freezes. Just restart the airplane while it's flying halfway through the air. We're going to come back later and collect the people who died. You can't do that. We have to do a proper thing over here. You can't do that. That's not going to happen. That's it. You can do it with your wireless modem. But that submarine that is under the water, you cannot reboot it and hope for everybody to survive. Okay? All right, so that's that. Okay, so now how do we do it? Let's do it. So you saw the syntax. It's pretty simple and straightforward. I'm just going to go right off the bat and do it for you. So we're going to write the program that it's going to print everything in reverse order in 2 seconds. Okay? So what do? I need a pointer for the array, so I'm going to say integer array, an integer pointer array. Remember, first rule of dynamic memory allocation. Any pointer that is not used, you make it null, so you can recognize it's not being used. That's the most important aspect. You should write it down, stick it to the wall. Every morning you wake up, set the pointer to null. You have to see that, always. If the pointer is not used, you set it to null. And how do you write it? You write null PTR. You always do that. Now, I need to know how many integers, right? So I'm going to say integer num. And set that one to 0 for now. I like to set everything to 0. Then I'm going to say cout how many integers. OK? So I'm going to ask how many integers. Then I'm going to get the integers. So now I have the integers in hand. Now that I know how many integers I have, I'm going to say array is equal to new integer num. That's when my array is getting created, while the program is running. And now I want to print them in reverse order. I'll go for integer I set to 0, I less than num. Actually, I'll set to num minus 1, and I greater than or equal to 0, and num minus minus. I'll do it reverse one, right? In here, I'm going to say cout array cout array I, and put a space between the two, and I'm going to go cout and L. Go to new line. If I run the program now, I'm going to have memory leak. Write it like this. Run it the way I told you in a workshop with Valgrind, or whatever you call it. You will see that it's going to say these many leaks possible. Like you have these many bytes lost in your memory, yada, yada, yada. Okay, it writes that. So you got to make sure that you have that. You have to make sure that you actually wipe it out. So after we are done, now I have to say delete array. And remember, however you create, that's how you delete. You understand that? However you create, that's how you delete. Just for fun of it, I'm going to make this integer dynamic too. One integer. Crazy thing to do. Nuts. But I'm doing it. I'm just going to create one dynamic integer, not an array. What do? I'm going to say integer pointer num is equal to new int. And that's it. Nothing else. Just one integer. One integer. And in here, instead of having that, so I'm writing this fully dynamically. So in here, I'm going to say target of num. And in here, I'm going to say target of num. And in here, I'm going to say target of num and target of num. And now at the end, when I'm deleting, I'm going to delete the num exactly how I created. This one doesn't have square bracket because it doesn't have square bracket. This one does have square bracket because it's created by a square bracket. So in this program, all my variables are dynamic. None of them are done statically allocated. None of them are statically allocated. A statically allocated program is the program that you have stuff in your executable, like regular variable. Like this, everything's set. So if we run this step by step, this is what happens behind the scene. Put this at left, put this at right. So it starts. Can you see that code? Hey, can you see that code? The code is visible? Okay, just want to make sure we're okay. All right, so now it runs that. And as you say, array is null. And num is not null because it immediately creates it. So it actually shows an address. So this address that you see over here is in num. You see it shows negative. Don't worry about the negative value. It's not negative because I'll explain later, but it is an address. If it's not 0, it's an address. Negatives don't mean anything. It doesn't know that. Anyways, don't worry. That's something that you need to know about binaries. Now we're going to say how many integers. So it's going to say how many integers. I'm going to say over here, and it's going to run and wait for me to get it. Now in here, I'm going to say 5. Now if you see num is garbage, but when you do this, it shows that it's actually having 5 in there. You see that? So it says the address is that, but there is 5 in it. Are we good? Now that we have it, now this array, it's all garbage. You see that? There's nothing in it. But as soon as this address is not pointing to anything. It's null. But as soon as I do that, now it has 5 integers. You won't be able to see anything. Again, it's C language. It doesn't know how many you have. It just knows at the beginning it's a pointer. We know that it's an array, and that's why we are dealing with it. There is no way that the program can differentiate between num and array. They are both pointers. This one is pointing to only one. This one is pointing to many. We know that because we designed it. That's how it works. Then in here, I'm gonna start. Oh, I forgot to get the numbers. I'm printing garbages. I forgot to receive the numbers from the user. Idiot. One more time. I was so excited that I did it. OK, so let me just do that. So now in here, I'm going to say cout enter the numbers. Write another loop for integer I set to 0, I less than num and I plus plus. You know that these two i's are completely different variables, right? The first one gets created in the first loop and dies, and then the second one is created and it dies. These two i's, their scope is the for loop, okay? If you want to have it separate, you have to put a separate I in there. I'm not doing that. So in here, I'm going to say cout. I'm going to show I plus 1. And like that to enter it. Now I'm going to say cin into array I. And I'm going to read them one by one. We good? Oh, and this num plus plus is wrong. It has to go like this, because minus minus is more powerful than that one. I think we're good. Are we okay? I think we're okay. So I'm going to come right down to here. As you see, I'll put a stop sign over here. You see that? Now I'm going to run it. It runs through this and stops at here. Okay? I'm pressing F5, which is essentially this. If I go to debug, you see F5 start debugging. So I'm pressing F5. It runs. Says how many integers? I'll make it 3. I don't want to have 5 over there. So I'm going to put 3 over here, and I hit enter. So 3 integers created. Enter the numbers. One by one, I'm going to enter it. So that's going to be a 100, and then 200, and then 300, and it comes out. Now it comes over here and starts from the last one. So I starts from 2. As you see, it prints 300, again 300, again 300. Why? Because I forgot to reduce I by 1. I did num by 1. I don't know why. If after 20 years of programming, I make stupid mistakes like that, see how many mistakes you're going to make. So be happy. Don't worry about making mistakes. We'll fix it afterwards. So I'll stop. I'll go one more time. And that's one of the reasons that I do things live, because you see the mistakes I make, and I'm going to fix it in front of you, and then we'll continue after that. And if anybody can catch my mistakes before I compile it, you get extra bonus marks for your midterm. Remember that. So if somebody would have told me, hey, Farda, that's not num, it should be I minus minus, you would have received 2% for your midterm. Remember that. Okay? I do lots of stuff like that. Okay, so let's run it one more time. So again, 3, 100, 200, 300. Now it comes over here. So that's 300, and then 200, and then 100, and it comes out. Now the array has values. You see that? As soon as I delete it, values are no more. It becomes garbage. I gave it back to memory. You see num has 3 in it. As soon as I delete it, it's used by someone else now. It's garbage, and it's gone. Now this program doesn't have memory. Are we okay with this? Are we okay with this? That's syntax for dynamic memory allocation. I just showed 2 plus 2 is 4. Now I'm going to say, let's make a spacecraft to go to Mars. Okay? So it's going to be like that. So with this, you can do so many things. Okay? This is essentially the gist of dynamic memory allocation. But how actually we can make it work, you'll see. And then after it's done, it comes out and everything's good. Questions? Questions? The class ends at 1:25, right? 1:25. It means I can give you 5 minutes break before I fry your brains, okay? I'll give you a break. So if I have 10 minutes, you come back at 50, then we have half an hour. Yeah, but please, 10 minutes, no more, okay? 10 minutes break. I'll pause it. Please remind me to resume recording afterwards. Because we are doing lecture this lab, I have done an extension to see exactly when the extensions are. You go tilde farda.suleimanlu/suleimanlu/submit, and then 244 W1 lab NAA-do. Okay? It's going to tell you exactly what the due date is. So it's going to be tomorrow midnight on time, Sunday midnight rejected. Okay? You have till tomorrow night to submit it. And this, for the reference, it's going to be the 27th. Okay? Also, I need to remove the restriction for location submission. I'm going to bring it down. And there you go. Now you can submit it from anywhere. Again, the submissions the submissions you're giving is going to get compared to all students in OOP244 and BTB200. Be careful. Okay? Don't copy. Yes?
Yeah, I have to show you on my laptop.
Give me a second. So that's that. Restrictions removed. Let me pause again. Yes?
What are the instructions exactly for what's in the lab? Because I opened the lab for tomorrow.
One more time?
I opened the lab for tomorrow and I didn't get like what I exactly are the instructions. What are the instructions?
Where are the instructions for the lab? You go to Blackboard. courses, OOP244. Not course information. Let me add something over here. Anyways, it is the Seneca organization OOP workshops. I'm going to create a link for it over there. So I thought everybody got that. So I'm going to add something over here. I'm going to call it workshops. Course information. Yeah, organization. So again, you go over here, and then you're going to have workshops. Then in workshops, you click on workshop 1, and these are the instructions for workshop 1. Is that what you're talking about?
Yeah, but like it says like up to the
You have to read to the end. That citation comes over here. It tells about all that. Then it's going to say coding style, all the stuff there. Or part 1 workshop. C style, compilation safeguards, adding C style functions, your task, what to do. Everything's there. You have to read it to the end. Okay, I'm going to remove those things and put it separately, and so you don't have too many things at the beginning of the workshop. But you have to read it to the end. Okay, all right. Anyways, all right. So now let's actually take a look at it and see what is that. What that kind of summarize what we've talked about. So to do dynamic memory allocations, you have to first create a pointer. So we are going through the syntax one more time in detail. So you create a data pointer, anything you want to point to. And the type can be anything, integer, character, carb, employee, table, chair, whatever it is. It creates that one. And by the way, all these things are in the notes. You don't need to take a picture. It's already, the whole presentation is in the notes. The reason if you're welcome to take a picture, by all means, do it. But there are so many slides that, anyways. So when you set that, you cannot just use it, because if you use it, it's set to null, it's going to crash. So one of the most important, like one of the things that you know, if that the data pointer is just created, it has some garbage value, and the target is some whatever the garbage value is pointing. So if you use it, you're going to get a null pointer assignment, segmentation fault, or anything like that, and that's not going to work. You have to allocate memory. Set the pointer to the type that it points to, and you put the data size that you have. And you always keep track of what is your data size. So you have a data size, you have a type, new, and it creates it. Always stay within the size of the data size. If you exceed even one character, one space further, it's going to crash you. If you stay within, you're good. Okay? After you are done, always delete how you created. If you create it as an array, you put square bracket. If it's a single entity, you just put nothing. And then you delete it. And then you're done. Now, what are the things you need to be careful about? Number 1, null pointer. When data is just created, you cannot just use it. You have to do dynamic memory allocation. That's the first thing that you're going to get. So if your data is null, if the pointer is null, you cannot use it. Okay? You have to first allocate it. Stay within the size. We talked about it. So make sure you are not passing off the target of the size. Not at all. You're talking about a character, or you're talking about C string. C string. There is no such thing as \0. \0 is only a standard, something that programmers talk with each other only for character strings, not even for character arrays. You may have a series of characters in an array that is not a string. If that's the case, then if you have 5 characters, you have 5 characters. But if you want to use this character with the standard string library to be able to print and read and stuff like that, then there is a convention. There is a standard that all programmers agreed on, saying because C doesn't know what is the size of a character array, we null terminate it. It means it's the end of data. But that's only for character arrays. It has nothing to do with anything else. And it's only for character arrays who are considered as strings. So when we say a C string, it means there is a rule you have to follow, which means end of data is with a null termination. Okay? Make sure if your data is pointing to something and you have something new to allocate, to delete the old one. If you just set a new piece of memory to an already existing one that is pointing to something, that means memory leak. Never do that. Okay? It is extremely important. When you are using a piece of memory, before you want to allocate, always delete it, to make sure it's not pointing to anything. Otherwise, it's just going to point to something new, and you're going to lose what you have forever. That's one of the most common ways to have memory leak. Next thing. Yeah, so that's memory leak. Correct state of an unused pointer is always null. So if you have a pointer that is not used, you set it to null. If you delete something, immediately afterwards set it to null, because it's not used anymore. It should be your habit until you get a full grasp of what dynamic memory allocation is. And then after that, you know when to set it to null and not to. For now, when you create a pointer, you set it to null. When you delete a pointer, you set it to null. Unused pointers must be always null. It's something that you have to follow. Whenever you are allocating memory, you have to make sure that the memory allocated is kept track of. So if it's 7, you have to set some place that you know, some kind of a convention. How am I going to realize what is the size that I have? Okay, it's extremely important to do that. So usually when you are doing dynamic memory, tied to that dynamic memory, you have a size attribute that you keep your stuff in. That's extremely important. So you know what is the size of the things you have. And when you delete it, you have to delete it correctly. And after deletion, you have to set it back to null again. One of the reasons that everybody gets dynamic memory, it gets memory leakage without knowing. It follows the logic. Everything seems good, but you have memory leak is when you have an array and you delete it without square bracket. If you delete it without square bracket, it only deletes the first one because it doesn't know it's an array. Therefore, the rest of it will be memory leak. So you have to always make sure that the deletion happens the exact same when allocation happens. If you allocate it with like an array, you delete it like an array. When you allocate a single thing, you delete a single thing. Using pointers, always make sure they are not actually being used, which means deleting it is always a good idea. You can always, if you follow the standard and always set the pointer to null when it's not used, you can always check it to see if it's used or not. Okay? But for deleting, you don't need to worry. comfortably delete a pointer. If the pointer is null, delete will ignore it. It's not an error. So you can delete a null pointer with no error. But if it's pointing to something, then it's going to delete it. So remember, delete, set to null, always. You don't need to check to see if it has stuff in it. Just delete it. We don't need these two. We'll talk about it later. These two are not needed. I'm just going to delete them. Okay. And now that we know this, let's see how we can actually resize memory. How we actually resize a piece of memory. We have a memory, we want to make it bigger. We have a memory, we want to make it smaller. How do we resize things? Memory resizing happens like this. First, I'm going to show you visually how it's done, then I'm going to code it for you. Okay? So, as we mentioned, when you have dynamic memory allocation, you have a pointer that is pointing to a piece of memory, and you have a size that you are keeping track of how many things you allocated. That's how dynamic memory allocation works. Now, let's say that size is not big enough for you. If that size is not big enough for you, what do you need to do? You need to allocate bigger memory, right? For that, you cannot use mdata, because mdata is already pointing to the data you have. If you allocate memory in an mdata, you're going to lose the old one, because it overwrites it, right? Because of this, whenever you are resizing memory, you need to have a temporary memory, a temporary pointer of that type, and then allocate a new piece of memory for it. I have 7, I need 14, so what you do, you create a temporary pointer, you create the amount that you want, whatever the size is. Then, what you do, you copy everything from the old one to the new one. So everything that you have, you bring it to the new one, because you want the old data to be there. You don't want to lose it. After doing all that, now you can get rid of the old one. Now that it's copied, the old one is not needed, so you can delete that one. And when the mdata is deleted, it's not pointing to anywhere. But what is pointing to the new data? Temp, right? All you need to do is to take the address from the temp, put it in mdata. And obviously, you have to update that to 14, because it's not 7 anymore. So first thing we're going to do, make sure that that's 14. So first, we're going to make sure that the size is updated. Then we're going to copy the data, copy the pointer from the old one to the new one. So what happens, I simply get the value. See, I say mdata is equal to temp. It literally takes the address from the temp, puts it in mdata. So mdata is now pointing to the new memory. And then after this, when the program is over, this temp was a local variable, right? This is going to be gone when the procedure is done. That is gone, and after it's gone, what is left for you is a piece of memory with more data in it, and therefore it's resized. So again, step number 1, without bringing the slides, you have a piece of memory. You want to resize it. You create a temporary pointer. You allocate new one. You copy the old ones to the new one. You update the size. You delete the old one and make the pointer to point to the new allocated memory, and you're done. That's resizing memory. And that happens over and over. Many mistakes happen over here, like because students are used to deleting, because I say always make sure you delete the old memory, sometimes by mistake they delete the temp too. They think that if you do that, then you lose everything. Be careful. The temp thingy is actually, anyways. So let's do it. Yes.
You said
I think I'm recording. Yeah, I'm recording. You see it? If I didn't record, it would be very sad because I had to repeat everything the next day. Well, anyways, so let's have it over here. So I have integer data, pointer data, set to new int, and I'm going to put over here 4. So I have 4 integers. It's a dynamic array, right? And I'm going to say 4. Let's have an integer I over here just for the stuff we're going to use. So I'm going to say 4, I set to 0, I less than 10, and 4, and I plus plus. And I'm going to say data I is set to I plus 1 multiplied by, say, 10. So I'm just putting some values in there, okay? Just to see what I have over there, I'm going to create a function, void print. I'm going to say over here int values, or val, int size. And I'm going to say for int I set to 0, I less than size, and I plus plus. I'm going to print everything out. So I'm going to say if I is not equal to 0, print a comma, because I want it to be comma separated. It looks pretty. Then I'm going to say cout val I. And I'm going to say cout NL. So essentially, I'm showing all the data over there. Now in here, I can say print data, and I'm going to put 4 over here. So it's going to show the 4 values. And at the end, to make sure that I don't have dynamic memory allocation issues and memory leaks, I'm going to delete the data. Okay, so very simple thing. I have a dynamic data, set everything to multiplications of 10, and I want to print them and see what do I have. Run it to make sure I have some base to work with. And I have 10, 20, 30, and 40. It looks like it's printed properly. And you're good? All right? So now what I want to do, I want to resize this to more. How do I do that? Okay? To resize a piece of memory, what I can do is to create a function. So I'm going to call that function resize. It resizes, right? Or I can call it expand, right? And I'm going to get over here in this expansion that I have, in this expand of mine, I'm going to receive the address of a dynamic piece of memory, whatever it is. So in here, I'm going to say integer pointer the data, and integer size. Okay? And in here, I'm going to have integer new size. So you notice that I didn't return anything, right? You know what I'm going to return over there? The address of the newly allocated memory that has everything expanded. So in here, I'm going to say integer pointer. And I do like this. Now I can actually explain how it works. So I'm going to say over here, receives dynamic data and expands to new size. New size, then returns the newly allocated memory with new size. As easy as that. So this is dynamic data to be resized. This is old size. This is new size. This is newly allocated memory, newly resized allocated memory with new size and old data. So that's, if you use this, then you bring it over here, it actually tells exactly what the function is. Pretty cool way of actually doing it. So it exactly tells you what expand is doing. Parameters are these, returns these, so you can actually see what it does. This type of commenting is pretty good. So let's follow the steps. Number one, I need a temporary, before doing anything, I have to make sure that new size is bigger than size, right? Otherwise, there is no expansion happening here, right? So I'm going to say if new size is bigger than size, do this. Otherwise, there is no point of doing anything in here, right? So what I'm going to do in here, I'm going to say integer, pointer, new memory or new data, and I'm going to set it to the data, okay? And I'm going to return new data. So what happens here? If new size is bigger than size, my if happens, right? If new size is not bigger than the old size, it simply returns the good old thing that it had before. So nothing happens. It just returns the old thing that it had. It's not going to change anything. Everything remains the same. And the size remains the same, and we're done. Right? Now, so in here, I'm going to say if new size is not bigger, do nothing. Okay, now I'll come over here. Now the process happens. First, we need a temporary pointer to hold the data. Remember the steps. What are the steps, one by one? One, temp with new size. Right? Two, copy data. Three, delete old data. Four, reset. Four, delete all this, reset pointer. Okay? Reset pointer, which we don't have here. I'll tell you why. So now in here, actually, yeah, okay. So now what I'm going to do in here is this. I'm going to say integer pointer temp is set to new int, new size. So the temp with new size is created. Now I'm going to copy the old ones in here, right? So I'm going to say for integer I set to 0, I less than size, and I plus plus. Copy the old ones to the new ones. So I'm going to say over here, new data will be equal to the data, I in here, and I in here. One by one is going to copy everything. Right? So everything from the old data is going to get copied into new data. Now that I have everything, I can wipe the old one out. Now I'm going to say delete the data. Right? And I am sending the new data out because, oh, I don't have the new data. So now I'm going to say new data is set to temp. And I send the new data out. So this is logic that I don't like. I'm going to fix it soon. But this is something that I've written without using references, just pointers. So what I did over here was this. Now if I actually want to resize that, if I want to have 8 integers, I have to say data is equal to expand data for 8. This is what I need to do. So what happens is that it receives the data, deletes it, does all the copying, and the new thing is going back to the data, and data is resized. Now I have 8 of them. So this is a crappy one of doing it, bad way of doing it. The good way of doing it is actually using references. So now if I use this, I can write over here. For less than 8. Now I can say print data and 8. Let's run it, see if it crashes on us. Oh, it didn't copy the things, the first ones. What happened? Let me see. So it's getting the data, copying the new one. The old one is going to the new data, deletes the data. Oh, and yeah, and temp gets that one. And it lost the first one. Why did it lose it? Data. Let's walk through it. We have only 2 minutes. You know what? I don't want to. Let me try and fix the thing. I have only 2 minutes. Well, I was afraid of this thing to happen. Resizing, we'll start from scratch on the next session that you're coming in. But I'm just going to try to fix it in this 2 minutes. Okay? Give me a second and see what's going on. So we are all good with this. 1, 2, 3, 4. It goes over here. It prints that 1, which is fine. And now it goes to expand. It gets the data, puts it over there. It doesn't matter. Now it gets with 8. Starts from the beginning. 1 by 1, it's going to copy it. Yes. It's copied. Then it brings it over here. Oh. Temp, not new data. Sorry. Now it's better. Sorry. It was a temp. I was doing it in a temp. For some reason, I put it in new data. I'm supposed to copy it into temp because temp is the new data. I put it to the... That was my bad. OK, now it's fixed. OK, so let's run it one more time. So now if I run it, there we go. It's resized with a new one. And it's 125, and it's the end of data. So I'll put this one, assume that we did not do this. Go through it, walk through it like I did, see how it's working, and get one of those 4-colored pens, okay? And when it says a pointer, draw a circle. When it allocates memory, allocate the memory for it, draw an arrow. Walk through it like that step by step and see how it works. That's your task for Monday. Monday, you're going to come. I'm going to complete the whole thing and be done with it. OK? Yes, of course. Oh, yeah. Pen and paper is your friend. Don't use computers. So put this code in front of you, OK? And take a piece of paper with a 4-colored pen and follow the steps exactly. So when you see a variable is created, create a variable. When you see when in here you see a function is actually being called, do it exactly as I mentioned to you. So when this is called, put the prototype over here like this, and put it in front of it, and right over here, exactly how I explained. So right over here equals data. This size is equal 4. This size is equal 8. And run it like this, exactly as I told you. Walk through it like this and see how it works. And if you can follow through, then you're going to be good. Okay? It's extremely important. I'll do it the next day you are coming in. Okay? All right. But please do so. Go back home and do it. I'm going to right now save everything. Save. Of course, right now, in 3 seconds. So I'm just going to go right now to OOP244 and right-click over here, commit. DMA part 1. So the next day you are coming in, it's got to be part 2, commit and push. It is in the repository right now, and the recording is in the session. Also, I'm going to put it on YouTube. Have a good day, everyone.